All right, in this video, we're going to be talking about intermolecular forces. So remember, when we're talking about intermolecular forces, we're talking about the force of attraction that exists between two separate molecules. Now, in this video, we're going to be looking at pure substances. So in this case, both molecules will be the same. So here are the type of intermolecular forces that we talked about in class, and I've arranged them from weakest at the bottom to strongest at the top. Now, I'm going to say a little bit about each one of these, but it's not going to be a comprehensive review. So London dispersion forces are the result of temporary instantaneous dipole moments. And these occur when the electrons are moving around in the electron cloud. So if I use the helium atom as an example, helium consists of a +2 nucleus, and then it's got 2 electrons. And if the 2 electrons happen to find themselves on the same side of the atom, that side will become partially negative temporarily, and the other side will become partially positive, also temporarily. But if this helium atom that has this temporary dipole moment, where I've got a partial negative and a partial positive charge, the electrons on this atom will be attracted to the positive end. And so that will induce a temporary dipole moment in this neighboring helium atom. And so now these temporary partial negative and partial charges attract each other, and we have this very short temporary interaction. Now, all molecules experience dispersion forces because they all have electrons that are moving around. But if I have 2 molecules that are both nonpolar, then all they have are dispersion forces in terms of intermolecular forces. So dipole-dipole interactions occur when I have a polar molecule. And so when molecules are polar, they're said to have dipole moments. And these terms are essentially synonyms, so that's where the name comes from. Right? I have a dipole moment on one molecule interacting with a dipole moment on another, and so we call it a dipole-dipole interaction. So an example of a polar molecule is acetone. I have the polar carbon-oxygen bond. It's asymmetric. There's nothing to cancel out the pull of that one oxygen for the electrons. And so when I look at acetone, the oxygen end will be partially negative, and the other end of the molecule will be partially positive. Now the big difference here between dipole-dipole and London dispersion forces is these are also partial charges, but they're permanent partial charges. So they always exist, whereas in the London dispersion forces, the dipole moments only exist for a tiny fraction of a second. But when I have 2 polar molecules, the negative end of one is going to be attracted to the positive end of the other, and that's the nature of the dipole-dipole interaction. Hydrogen bonding is actually a special type of dipole-dipole interaction. So if I have 2 polar molecules, and they meet these 2 criteria, then essentially I upgrade the dipole-dipole interaction to this special type of dipole-dipole interaction that we call hydrogen bonding. So hydrogen bonding will occur if one molecule is polar and I have a covalent bond between hydrogen and an oxygen, nitrogen, or fluorine atom. And then the second molecule doesn't have to have hydrogen at all, it just has to be polar and have an oxygen, nitrogen, or fluorine. When this happens, the partial negative and partial positive charges are bigger, their magnitude is greater than normal. And so the intermolecular force, the attraction between the two, is much stronger than a regular dipole-dipole interaction. And so that's why it gets its own sort of special category. So water is an example of a molecule that has hydrogen bonding, because I have a hydrogen covalently bonded to an oxygen in one molecule, and another molecule is obviously polar and contains oxygen. Ion-dipole interactions occur between an ion and a polar molecule. So in order to have ion-dipole interactions, I have to have a mixture, because I need both a polar compound and an ionic compound. And so we actually won't encounter these in any of the examples in this video. All right, finally, I just want to say a word about ionic bonds. And so these aren't traditional intermolecular forces, because ionic compounds don't have molecules. So if you don't have molecules, you can't really have intermolecular or intramolecular forces. However, ionic bonds are kind of both. So they're both short range, like intramolecular forces, and long range, like intermolecular forces. And also like intermolecular forces in covalent compounds, ionic bonds are what govern the properties of the condensed phases. By condensed phases, I mean solids and liquids. The reason ionic compounds are solids is because they have these strong ionic interactions. And so I may ask you what types of intermolecular forces exist in an ionic compound, And the answer that I would give for those is that they have ion-ion interactions, or we could just say the ionic bonds are basically intermolecular forces. Okay, so if I give you a compound, or if I'm given a compound and I want to determine what types of intermolecular forces it has, this is the way I think about it. So I ask myself a couple questions. First question, is the compound ionic or covalent? If it's ionic, then the strongest intermolecular force is the ion-ion interactions, or the ionic bonds. If it's covalent, I have a little bit more work to do. If it's covalent, I need to decide is the molecule polar or nonpolar. If it's nonpolar, then all it has is dispersion forces. If the molecule is polar, then it also has dipole-dipole interactions. And then finally, if I decide that a molecule is polar, does it meet the criteria to have hydrogen bonding? So let's look at a couple examples. The first one is carbon dioxide. So my first question, is it ionic or covalent? And it's covalent. So now I need to know, is it polar or nonpolar? So I need to draw the Lewis structure. There's the Lewis structure. And so I have polar bonds, but because the geometry is linear and the oxygens are arranged symmetrically around the carbon atom, their pull on the electrons will essentially cancel out, and so the molecule is nonpolar. So the type of intermolecular forces, because it's nonpolar, all it will have is dispersion forces. Next example is ethanol. And so my first question, ionic or covalent? And it is covalent, so I need the Lewis structure. If you're ever on a quiz or a test and you're not sure how the atoms are connected when I have multiple central atoms, don't hesitate to ask me. All right, but this is the Lewis structure for ethanol. So now I need to know, because it's covalent, I need to know if it's polar or nonpolar. I've got polar bonds. The geometry on this oxygen atom is bent, and so it's going to be asymmetric. So I've got polar bonds. It's asymmetric, and so it's going to be polar. So I know it has dispersion forces, because everything has dispersion forces. Because it's polar, I also know it has dipole-dipole interactions. And then I also want to check to see if I can upgrade the dipole-dipole interactions to hydrogen bonding. And so because I have a hydrogen covalently bonded to an oxygen or nitrogen or fluorine in one molecule, in a second molecule it's polar and I have an oxygen atom, so I can upgrade my dipole-dipole interactions to hydrogen bonding. So I have hydrogen bonding, dipole-dipole interactions, and dispersion forces in between two ethanol molecules. The next example is ammonium nitrate. So this is where your polyatomic ions come in handy. So ammonium nitrate is NH4NO3. But even though this is all nonmetals, it is ionic because I have an ammonium ion, NH4+, and I have a nitrate ion, NO3-, so it is ionic. And so if it's ionic, and I ask about the intermolecular forces, it has the ionic bond or the ion-ion interaction, and then of course everything has dispersion forces. Okay, the next example is CF3H. So I need to ask, is it ionic or covalent? And it's covalent. Here's the Lewis structure. I need to ask if it's polar or nonpolar. So fluorine being the most electronegative element on the periodic table, these fluorine-carbon bonds are definitely polar. And it's asymmetric because I've got fluorines in 3 positions of the tetrahedral geometry, but hydrogen in the other. So I have polar bonds and it's asymmetric. So it's definitely polar. And so this molecule will have dispersion forces. There will be dipole-dipole interactions between the two. And then I should check to see if I can upgrade it to hydrogen bonding. In this case, I can't, because even though it has both fluorine and hydrogen, the hydrogen is not connected to the fluorine. So my intermolecular forces are just dispersion and dipole-dipole. All right, in our final example, we want to know what types of intermolecular forces exist in a sample of propane. Propane is C3H8. And so I ask, is it ionic or covalent? And of course, it's covalent. And then I need to know, is it polar or nonpolar? Now, in this case, I don't even have to draw the Lewis structure, because remember, when I have compounds that just contain carbon and hydrogen, I don't have any polar bonds. So I know it's nonpolar. If it's nonpolar, it will only have dispersion forces for the intermolecular forces.